Welcome to chapter 8. In this chapter, we will discuss on-chip networks. So we need three specific pieces of background. So the first is pipelining. Uh, we don't need a lot of pipelining, but at least in order pipeline part, that's the reason of chapter 2 over here. Caches definitely, and some idea of graph theory. Very simple, but still at least some idea is needed. So here is how we will proceed. So we'll have 6 sections. So we'll start with an overview of an NOC, discuss basic ideas in message transmission, message routing. So routing basically means how do you move a message from one part of the chip to another part of the chip, the design of a router. Then once we have covered the basic NOC, so the network on chip is also known as an NOC, capital N, small o, and capital C. So once these four have been done, we will look at an advanced topic, which is the design of a new kind of a cache architecture known as a non-uniform cache architecture. And finally, we will conclude with discussing the performance aspects of NOCs. So let's first take a look at the layout of a modern chip. So there are two kinds of popular layouts. The first kind is this chessboard kind of layout, where as you can see, we have cores, we have cache banks. So go back to chapter 7. So in chapter 7, we had discussed more about cache banks. So the idea was that we will have multiple cache banks in a large cache. So typically the last level cache, whatever it is, L2, L3, L4, doesn't matter. We refer to it as an LLC. Last level cache, LLC. So the cache banks of the LLC are distributed throughout in this case. And additionally, we have memory controllers. So all of them have to be connected on the on-chip network such that they can talk to each other or communicate with each other. Another popular layout is this rim kind of layout, where you have a mix of cores, cache banks, and memory controllers which are on the rim, and everything else is in the center, which means the cache banks, I'm sorry, stand corrected. So the cores and memory controllers are on the rim, and the cache banks are in the center. So this is another kind of layout, but clearly, many other kinds of layouts are also possible. And there is, of course, a trade-off in terms of performance, as we will see. But regardless of the layout, the on-chip network has to connect all of them. So now let's come to the definition of a node. So in any network, we will always have two terms, a node and a link. A link can also be referred to as an edge if particularly we are drawing the network like a graph. So this is the computer science graph. It's not the regular engineering graph. So the graph is a data structure. If you have not heard about this, then stop here, stop the video here, read about graphs, what they are in a computer science data structure terminology, and then come back. So coming back to the definition of a node, it is any kind of an object or any entity that can send or receive a message, which in our case could be a core, a cache bank, a memory controller, or an accelerator. An accelerator is a specialized circuit, such as an AI engine or a graphics engine, which does a specific task, right? Is a specialized compute engine. So now we will define the term called a router, which is central to our discussion on-chip networks. So every communicating node, in a sense, every node that wishes to communicate has a router. The router is nothing but its communication subsystem that orchestrates the communication on its behalf. So in this case, routers are, of course, are connected to other routers. In a certain sense, a router represents a node in the communication subsystem. It is connected to other routers, and then there are channels between routers. So a channel is a combination of two things. So we have a physical part to a channel, which let's say between two routers would be a set of copper wires. So that's the physical part of the channel. And furthermore, at the entry. So the entry is also called the ingress. So this is just the input entry, right? So we have two terms, ingress and egress. So egress is the exit and ingress is the input, is the entry. So along with these copper wires, we have data buffers. So data buffers are nothing but small, it's a small storage area for storing in-flight messages. So the key operative term over here is the term data buffer, which is to store in-flight messages of the channel. So a channel, as I said, is more than a set of parallel copper wires. Is a set of parallel copper wires along with these data buffers that are there at the ingress or the entry of every router. So in a sense, messages come here, they are buffered in the data buffers, and then subsequently they are processed in the router. So how would the router process it? Well, it is connected to other routers. So it will decide where to send the messages, to send them here or to send them here. So how do the routers communicate with each other? This is again a basic question that needs to be answered. So let's look at some very basic concepts. So let's first consider two routers. Let it be router R1 over here and router R2 over here. So let us look at the wire between them. So the wire in this case, as we have said, in a simple avatar is basically a set of parallel copper wires between the source and the receiver. So let's just consider them as normal wires. So there are no buffers in between the wires, unbuffered. So what we have seen in our discussion on the Elmore delay model is that the transmission delay on the wire is proportional to the square of the length of the wire. So it's quadratically related. So if D is the delay and L is the length of the wire, then there is a quadratic relationship like this, which means that long wires are very slow because you double the length of a wire and the propagation delay of the signal on the wire increases by 4 times. You increase the delay of the wire by, let's say, sorry, you make the wire 3 times longer and the delay becomes 9 times. So this is an issue. So because this is an issue, what we can do is we can take a large wire and divide it into S segments. So when we divide it into these segments, what do we do between two segments? We insert a buffer. The idea of the buffer is to basically store and forward. It's like a relay. So it's not storing the entire thing, it's getting some data and immediately forwarding to the next. So it's like a pipeline in that sense. And clearly, it doesn't have a great amount of internal storage, nor does it need to have. Its main idea is to kind of read in and then write out. So, this somewhat simple idea, if we look at it mathematically, we will see that there is a big benefit. So, let's understand this. Let the delay of one of these buffers be small d. So, for x segments, how many buffers do we need? S minus 1. And the combined delay of all the buffers, because they form a series system, is s minus 1 multiplied with d. Furthermore, we have s segments, and the delay of a segment, delay of a signal, the time that a signal takes to traverse a segment is proportional to, so if kappa is a proportionality constant, is proportional to the length of the segment, which is nothing but L by S, because L is the overall length and we have S segments. So the length of each segment is L by S, so it's kappa L square by S square. And as you can see, the final expression turns out to be this. So here, what is the variable? The variable is the number of segments. All right. And what we can do is, given the fact that we can optimize the delay against this variable, we can differentiate this with respect to S and set it to 0. So in this case, we'll get an extrema and it will turn out to be the minimum. I'm omitting that proof. But the key idea is if we solve this expression, then S will become equal to square root of kappa by d into L. So the most important thing is that the optimal number of segments, which minimizes the delay of the entire wire, right, of the entire channels. In this case, a channel is a more intelligent thing because it has buffers within it. The optimal number of segments is proportional to the length. And furthermore, if I plug in the formula for the optimal number of segments into this expression, I get the optimized delay to be 2 square root of kappa d multiplied with L minus d. So what is the takeaway over here? The key takeaway over here is that unlike the previous example, where the delay was proportional to the square of the length of the wire, in this case, the delay is more or less approximately proportional to L. Right? Of course, you have this minus d over here, but by and large, we have reduced a quadratic relationship into a linear relationship. Right? So this is why we have created the idea of this buffered link. So link, as I said, is nothing but the connection between nodes. In this case, it's a connection between routers. So a buffered link has a linear delay and is linear in terms of the length of the link. Now let's look a little bit more at the way the links are organized, physically organized on the VLSI chip. So we need to understand that a VLSI chip is made of multiple layers like a multi-story building. The lowest layer comprises the transistors, right? So you'll have, the transistors actually look like a plus sign on silicon because you have one polysilicon layer over doped silicon. So let's refer to them as a plus. So the lower layer is full of transistors. The lowest layer actually is full of transistors, so there is no space left. If I want to connect one transistor with the other, so what I do is that I add a layer on top which only has metallic connections. So what I do is that I go up. On this layer I traverse and then finally I go down. So as you can see, this is like, traversing a multi-story building with lot of staircases across floors. So if I want to go from, let's say, this point over here to this point, then I need to use multiple metallic layers, right? Or let's say, let me change this point. I mean, this is maybe easier to visualize. So what I do is that my connections are kind of complicated. So the signal goes up like this, then goes like this, then goes like this, then it comes here, then it comes down over here. So what you can see is that any kind of a signal transmission between one transistor to another, the wires are not in 2D space, they're in 3D space. And furthermore, we have multiple metallic layers in the sense, we have one layer like this, one more layer, then one layer, then one more layer, and so on. Because even though the lowest layer is comprised of transistors, but the layers on top are only for the interconnection. So these are like overpasses on highways, right? These are like flyovers and overpasses and so on. Where the idea is that you traverse a 3D route to go from one point to another on the 2D plane. The reason you can't do it on the 2D plane is because there is no space. And why do you need multiple metallic layers? Well, the pattern is hidden in this diagram. So if you see, the patterns are like this, that in one layer, all the wires are horizontally aligned. Then in the next layer, they are vertically aligned. So horizontal and vertical in the sense one is along the x-axis, one is along the y-axis, again along the x-axis, again along the y-axis, so on and so forth. The reason for this is that you cannot have an intersection of wires on a layer, right? So two copper wires can never intersect, otherwise they'll have the same potential, so intersections are not allowed. So that's the reason we alternate. So what we do is that we have multiple metallic layers and all the wires in a metallic layer are broadly along the same direction. So they are either oriented along the x-axis or along the y-axis. And the connections are made in such a way that if I want to connect 2 points, then they actually go via multiple layers using this 3D geometry that you have seen. And of course, this is static, it's not dynamic in the sense it does not change. But nonetheless, the connections are complicated, and this is a dynamic. Sorry, I'm sorry. This is statically determined, but again, it is 3D. So one term that needs to be introduced over here is the notion of a via. It's also called a TSV or a trans silicon via because it connects two layers, connects wires on two layers, right? So it's literally a vertical connection. So using a combination of wires and wires, we achieve connections between transistors. So if you think about it for a modern chip, you can have billions of transistors, let's say 2 billion transistors. And then again, they are divided into cores and functional units within the cores. See, if let's say one functional unit over here, let's say an adder wants to communicate with another unit over here, then you have to send wires from here to here. And sending wires would essentially amount to going up and down different metallic layers. So we would typically have one transistor layer and 10 to 15 metallic layers just for achieving the connections. And then we would have a few special layers. So of course, one special layer would be the power layer, which is to provide the power connections to all the transistors. So in this case, also you would have huge trans silicon wires going down. So these wires would basically provide power to the transistors. So it's a the power layer is organized as a grid. So we'll discuss more of that in a later chapter, the chapter on reliability. And then we can have another layer for ground connections, right, which is the return path of the current, and one more layer for the clock, for routing the clock. So these are three special metallic layers, right? So I'm not drawing the full rectangle, just the line. And then we have regular metallic layers to achieve connections. And then, of course, we have one layer that is full of transistors. So that is where all of your logic and memory, etc., everything is implemented. But of course, the wires go to other layers. So we can have three kinds of interconnects in silicon chips. We can have local wires, which are used to connect transistors within the same functional unit, which means within an adder or within a multiplier. Intermediate wires are across functional units, but maybe close by. And global wires are literally end-to-end wires. So as we have seen, intermediate and global wires are typically buffered. In a sense, we have buffers in between them. But since local wires are short, there is no need to introduce buffers within them. So let's first look at a very simple yet naive solution for connecting all the routers, right? So this is a design that we have seen in many other places also, which is that all of them share the same set of copper wires. So the same set of shared copper wires, this is known as a bus. Even though this design is extremely simple, but still it does have its fair share of shortcomings. So the biggest shortcoming is that we can have only a single transmitter at a time because multiple transmissions are not possible. That would lead to interference. So we could have one sender and we could have multiple receivers, but again, one sender and multiple receiver kind of traffic is not very common in our systems, in our multi-core systems. Furthermore, you need a dedicated circuit called a bus master that receives requests from multiple senders. So multiple nodes would say that, look, I want to send, and the bus master would give one of them permission. So that also is needed. But in any case, this is a sequential bottleneck where only one sender can be alive at a time, can be sending at a time. And also the bus master is a point of contention. Hence, this idea is slow and it is not scalable. In a sense, it will not scale to many, many cores. So that is not going to happen. So that is the reason there is a need for a more complex topology. So that you would have realized up till now. So the layout of a multi-core processor would look like this. So this again, I've taken the basic chessboard design of cores and cache banks. We have memory controllers at both the ends. So we have memory controllers over here and we have memory controllers over here. And then we have routers. So the routers are representative of one tile, where a tile in this case is actually encompassing two cores, two cache banks, and a memory controller, five things. So we have one router per tile instead of one router per core or cache bank because we also wanted to minimize the number of routers. And furthermore, we don't have so much of traffic that we need so many routers. So some coalescing has been done. So what we have basically done is we have divided the set of communicating nodes into tiles, right? And then basically for one group of cores and cache banks, we have actually treated all of it as one node and given it one router. And the routers need to be connected in a given topology such that effective message transfer is possible, right? So the key idea is that we have the notion of tiles, one router per tile, and the routers are connected. These are the three take home points from this video. So if you want, you can just, go 30 seconds back and just listen to what I said once again. Now, the nodes, as I said, are organized as tiles. We have one router per tile which manages the process of sending and receiving messages. Furthermore, if let's say the routers are connected as a mesh, the job of a router is to send and receive messages on behalf of its local tile, as well as, right? So this is important, as well as forward messages that have originated from other tiles. So it also does the job of relaying messages that have originated from other tiles and other routers. So in our case, the routers will be referred to as nodes and adjacent nodes will be connected with links. The routers and links will form an on-chip network. So let us now look a little bit at on-chip networks and we will discuss two terms which are of vital importance. The first is bisection bandwidth and the second is diameter. So consider an on-chip network like this. Okay, so let me connect them, right? So with links, so this basically a mesh that I'm creating. So the bisection bandwidth says that let's say how many links have to be snapped, right? So how many links have to be snapped to divide the NOC into two equal parts. So if this is the NOC and I want to snap links, then let's say that they are roughly equal parts. So we ignore small additive constants here and there. But the key idea is that how many links have to be snapped. Of course, if there are multiple ways of snapping links, we will choose, the the minimum out of them such that they are two equal parts. So let that be implicit in the definition that if there are multiple ways of snapping links, we choose the minimum one and to divide it into roughly two equal parts. So this is the bisection bandwidth. And what is the importance of this term, or let's say what is the value of defining it this way? What's the advantage? The advantage is that higher the bisection bandwidth, higher is the path diversity or the choice of paths between two nodes. So let's say you take one node over here, another node over here. Then if there are multiple paths that will get captured by the bisection bandwidth. And if there are multiple paths, the key advantage is that we can tolerate congestion better. Because if you just take a link, a chain kind of network like this, its bisection bandwidth is 1. Because its bisection bandwidth is 1, we can have a lot of congestion at any of these points. And since there are no other alternative paths, congestion can really slow a network down. So the same thing holds for a city network also, where the key idea is that if you have more parallel roads, there is less congestion, as opposed to having a single road and that road can lead to traffic congestion. So bisection bandwidth is the first metric via which we will evaluate a network. And the other metric is the diameter. So in the diameter, what we do is that we consider pairs of nodes. So let's say we consider this pair and that pair. So if we consider pairs of nodes, we look at the maximum optimal distance between any two pair of nodes. So what is the optimal distance? It is nothing but the shortest path, right? So you consider any two pair of nodes, we consider the shortest path between them, and we consider the largest such shortest path or largest optimal distance. That gives us an idea of the spread of the network, how large the network, or how large are the distances between two nodes in the network. So clearly our aim is to maximize the bisection bandwidth and to minimize the diameter. That is always our aim, that this is something that we would like to do. This is a desirable metric. This is something that we would like to do, which is maximize the bisection bandwidth, which means give a choice of alternative paths and furthermore minimize the diameter. So minimizing the diameter would basically mean that to go from any point to any other point, we don't have to traverse many links, we'll have to traverse fewer links, right? So you are kind of reducing the size of the network or the perceived size of the network by saying that, look, you want to go from any point to any point, you don't really have to traverse to many links. Because traversal through links, as we shall see, is the main determinant of the latency of the network, right? So that's the reason we want more connections between routers such that for any kind of traversal, we don't traverse many links, right? So these are our twin aims of doing this and doing that, right? This meaning bisection bandwidth reduction, and that meaning this meaning maximizing the bisection bandwidth, and that meaning minimizing the diameter. So let us look at a few example topologies. So the simplest topology that we can think of is a chain. So here all the nodes are connected one after the other as a linked list. So here, of course, the bisection bandwidth, as you can see, is 1. And the diameter is also fairly high. It is between this node over here and this node over there. So basically, the idea is that because the bisection bandwidth is on the lower side, there is no path diversity in the sense between any two nodes. There is only a single path. Whereas in the case of a ring, for instance, there is limited path diversity, which basically means that there are two paths. And so one path is from this point to this point, and the other path, from these 2 points is this way. So that's the reason the bisection bandwidth in this case is 2, and the diameter is also roughly half, right? So that's the reason a ring can still be seen, in occasional places in an NOC, but a chain you will almost never find, right? Other than, a few classical bus-based topologies where everything is connected. So that would be more like a star. It will not be a chain. So now let's come to the fat tree topology. The fat tree topology is interesting, but again, what we need to keep in mind is that this is more for cluster computers. It's not really for an on-chip NOC, so to speak. So what happens is that all the nodes are organized as a tree. So we have the leaf nodes. So the leaf nodes are actually the routers, right? So these ones over here are the leaf nodes. And then you have these bunch of internal nodes. So if, let's say from this node, if you want to send a message over here, the message goes up, 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 then goes like that. So, well, a natural question is that what is the bisection bandwidth of this network? Because the diameter is not much. So diameter is pretty much, log n going up to the root and log n again coming down. So you can say that it is roughly in the ballpark of 2 log n. Of course, it could be lower, maybe slightly lower given the constants, but it's roughly 2 log n. So looking at the bisection bandwidth, what we can see is that we can achieve kind of a clean cut over here. So if we kind of cut off the network over here, so let's say here, it appears the bisection bandwidth is just 1, which again is too low a value. This is not acceptable to us because as you can see, there is really no path diversity when we are going from here to here. That is the way that it would appear. But again, there is a catch over here. That's the reason this is called a fat tree and not a regular tree. So the idea is that initially, of course, the links are very thin. They are like a single link wide. But as we go up, the links become fatter and fatter. So basically here, if there are four nodes, we could have very well, four parallel links over here, which could be used for data transmission. So that is why it's a fat tree, because as we go up towards the root, the links become fatter. What does fatter mean? Which means that they can sustain more parallel flows per time. For example, you could actually have two wires over here. You could have four wires over there. So and then in that case, the bisection bandwidth is actually not that low. The reason being that as we go towards the root, we are increasing the width of these links. Hence, it becomes a factory. But as I said, the factory idea is great for cluster computers, not for on-chip networks. But what is there in on-chip networks is actually a mesh, where every node has a degree of 4. Other than, of course, the nodes at the corners or at the rim, which are essentially the nodes over here, right? So it is basically these nodes that have a degree, 2 in one case and 3 in the other case. But otherwise, they are kind of 4 throughout. So the mesh is common. The other common topology that we have, so if I just go back to the mesh actually, what you would see is that this is a regular topology where this is easy to connect. It's kind of easy to construct on a chip because even otherwise, most of the connections between functional units resemble a mesh. So that's the reason the mesh is kind of easy to construct. And another topology that is easy to construct is a torus. And the torus you can see over here. Here, the idea is that there is no notion of a rim or corner defined in the sense that you have these cross connections between nodes, right? Uh, in the same column as well as nodes in the same row. So these cross connections exist. So these long links can cause an issue. So I'm not saying that it cannot cause an issue because the point is that the distance from here to here in terms of either, you know, the length of the wire or in the time it takes the signal to traverse. So, and plus the distance from here to here, right? If I just compare both of them, they are very different. So this is order n times more, assuming it's an n cross n torus. So this causes an issue, which basically means that if it takes one clock cycle to go from here to here, it is going to take more than one clock cycle to go from this node to this node, which again is not acceptable to us because our network in many ways does not remain a homogeneous network. So the long links are an issue. Even though every node has a degree of 4, so the issue with the rims and the corners being less connected, that issue is not that relevant, but nevertheless, the long wires cause an issue. Hence, we have the notion of the folded torus. So this is what I leave as a homework for the viewers of this video, which is that the problem of long links got solved. So what we have is that we still have a single row. So if you consider this row, we have 8 nodes here. This is a single row. So there are 8 nodes. As you can see, you count 1, 2, 3, 4, 5, 6, 7, and 8. They are connected. It is just that between two nodes, the length of a wire, the length of the wire segment, right, is twice of what it was in a normal mesh, right? And furthermore, the key point over here is that the length between any two of these nodes, right, is actually the same. So let's say between this and this, again, a small turn over here, this and this and this. And we do the same in the columns. So what you need to convince yourself is that this is still a torus. Of course, it is kind of folded in a different way. So visualizing that this network and this network are basically the same would require some amount of thought. But what I would like to convince you is that the notion of a row is still there in the sense that this is a row. The notion of a column is still there in the sense that this is a column. The nodes in a row are connected to each other, albeit in a slightly non-standard kind of way, where the alternate columns are kind of connected, this first and then this and so on. And again, in a column, alternate rows are connected. But again, the key idea by and large remains the same, that you have a mesh, right? You have the notion of rows and columns, you have a mesh, and you have these cross connections between corners. So basically, the entire thing is connected. It is just that in this case, you don't have long links, but the price that you pay is that between two nodes that are side by side, the length of the wire segment is actually twice of what it was over here. So here it was this much, and in this case, it is this much. But again, we are getting rid of long links. So folded torus by far is much more common. In fact, folding is a general network technique where we take a theoretical network and we kind of make it practical by slightly pushing, pulling, folding, stretching, reconnecting a network such that it is possible to actually realize it on a practical chip, right? Which is mostly a 2D structure, but could be a 3D with a few layers. Now let's come to high radix topologies. So the idea is that in a mesh and a torus, each node was connected to four neighbors, but in a high radix topology, they are typically connected to more than four neighbors, right? So which means there is additional path diversity. There is a somewhat low diameter because you have a heavy degree of connection. Yet it is hard to implement in an NOC. It's much easier to implement in a cluster computer. But that said and done, nowadays we are seeing instances of high radix topologies also come in. So we'll discuss hypercubes and Clos networks. A butterfly that has the way that we will explain will not be high radix, but it will kind of be a specialization of the Clos network, which is kind of practically implementable. It's just that we will require many more internal nodes known as switches. I'll describe that when we come to a butterfly. So let's first look at a hypercube. So hypercube is basically the generalization of a cube. So consider a hypercube of order 0. So hypercube of order 0 is a single point. To create a hypercube of order 1, we take two such single points and we connect them. So we have, 1 point here, we connect them. And we number one of them 0, we number one of them 1. So this is kind of a recursive construction. So what we do is that to create an hypercube of order 2 or H2, we take two copies of H1 as you can see. This is one copy of H1. This is one more copy of H1. And then what we do is that we preserve the original numbering scheme. As you can see, it is 0 here, 1 here, 0 here, 1 here. But the first copy, the most significant bit, we add a 0. So they become 0, 0, 0 and 0, 1. And for the second copy in the most significant bit, we add a 1. So one thing that you will quickly appreciate is that the Hamming distance, which is the number of bits that are different in corresponding positions, the Hamming distance is 1 between this node and this node, or between this node and this node. In fact, between any pair of neighbors, the Hamming distance is 1. So this is something that is easily observable, visible, and in a sense realizable over here. That by the way that we constructed this and the way that we numbered them, the Hamming distance is 1 between neighboring nodes. So now to create H3, which as you can see is a regular cube, the way that we define a cube typically, you take two copies of H2, all right? And after taking two copies of H2, so let us assume that the top face is one copy and the bottom face is one more copy. So let's say this is one copy here and this is one more copy here. So this is one H2 and this is the other H2. The corresponding nodes are connected. Okay. So why do I say that? Well, the least significant bits are 0, 1 here. The least significant bits are 0, 1 here. In H2, which is the layer on top, the most significant bit is 0. In H2, which is the layer in the bottom, the most significant bit is 1. All right. So at the top, it is 0. At the bottom, it is 1. And again, here, what you can see is that the Hamming distance between any two pair of nodes that are connected with an edge is 1. Why? Because see, within each copy of H2, that was already the case. And the way that we connected, which is by construction, we only add an edge if the least significant bits are the same, but they belong to two different smaller hypercubes. So in this case, only the most significant bit is different. So in one case, it is 0, other case, it is 1. So the Hamming distance is 1, right? So the key point is that the Hamming distance is 1. And again, to create H4, we take two copies of H3 and we connect corresponding nodes, as you can see, same numbering scheme. And again, the Hamming distance between adjacent nodes is 1. So this topology is a great idea for a network scale machine, for a cluster computer. It's great, right? There are no doubts about it that it's a great topology. But for the case of a regular on-chip network, it's not a great idea, right? But let's still look at its properties. So for hypercube with n nodes, the diameter will be log n to the base 2, right? So that is not very hard to see. As you can see, if you have 4 nodes, it is 2. Well, why? Well, the idea is if I have n nodes, so if there are n nodes, then basically every node can be represented with log n to the base 2 bits, which essentially means that in this binary encoding, we'll have log n to the base 2 bits. As you can see, log 8 to the base 2 is 3. And furthermore, the Hamming distance between two nodes is 1. So the maximum Hamming distance between any two nodes is again log n to the base 2 because every bit can be flipped, which is why the diameter is this and the bisection bandwidth is n by 2. Again, the reason being that, we have n by 2 nodes in each sub hypercube and each of them is connected with a link and that needs to be cut. So it is clearly a recursive data structure as we have seen. So I'll not spend more time repeating that. But we will go to the Clos network. The Clos network is kind of interesting. So it is basically a family of networks, and there you kind of define a broad structure of what the network would look like. So in this case, we have NR inputs and we have NR outputs, right? So let's look at what are the three parameters that define a Clos network or that parameterize the Clos network. So we can have a three-layer network, basically with three parameters R, M, and N. So as I said, in the first layer, we have R switches with N inputs each. So basically we have NR inputs. But NR inputs are divided like this, that we have R switches with N inputs each. And each switch has N inputs and M outputs. So in this case, both N and M are 4. So that is why we see 4 cross 4. So mind you, these switches are internal nodes. They are not really nodes that produce a message or that absorb a message. So they are purely internal nodes. And furthermore, there is a connection between input and output over here. So the key point really is over here that we are producing uh, R switches, right? So you're producing MR outputs over here at this stage. And furthermore, in the next stage, we have M switches. So, right, so we have M switches. Each switch has R inputs. And these R inputs basically come from one of the previous switches over here. So let's look at the previous round once again. So each one of them, right, given the fact that we have R switches, each switch will, so let's name them 1 to R over here. So what basically happens is that each of them we take one output each from each switch. So we'll have R outputs. They are connected to a switch. And each of these switches is an R cross R switch. And there are M such R cross R switches. So basically what happens is that this is an internal switch which basically connects or let's say routes an input to one of the outputs over here. And again in the final stage, we basically have a mirror inverse or we have a reversal of the first column. So the first column we had R n cross M switches. In this case, we will have R M cross N switches, right? So basically, it will kind of be a reversal of that. Where we will have, so basically we have MR outputs over here, so we will have MR inputs over here. And finally, we started with NR inputs. So we'll end this point with NR outputs. So we have NR inputs over here. We are ending at this point with NR outputs. So right, so NR in, NR out. Furthermore, the interesting part over here is that as you can see, just note how many of these switches we have. So to start with, we have R switches. Again, in the last layer, we have R switches. In the middle layer, we have M switches, where each switch is R cross R, right? So that's the idea. For different combinations of R, M, and N, of course, the network will look very different. But the basic idea is like this. You'll have three such columns of internal nodes or switches. And basically, with this, your messages can be routed. So I'm not saying this is the best idea for an on-chip network because you're adding many of these extra internal nodes or switches, right? So that is what it is called. Right, so that is what it is called, that these are called internal nodes or switches. And furthermore, what is the case over here? That these internal nodes are not, generating any new data or packet or even consuming a data or packet. Their only job is to kind of, route messages from one side to the other. So these have to be added, and they also appear to be in a centralized place, but of course, in a flattened Clos topologies where this is more distributed exist. But the key idea is this is still kind of a three-layer, it's kind of a three-layer circuit, right? It's a three-layer network. But the Clos network, as you can see, had three parameters R, M, and N. Where initially, as I said that we have R switches and then M switches. So if M is greater than equal to N, right? So basically, the three parameters, if M is just greater than equal to N, then there is a property, a mathematical property, which can be proven that we can always connect an unused input terminal. So let's say a new input comes. So it is assigned an unused input terminal to an unused output terminal, right? So this connection is possible if let's say an input is free and the output is free. But the idea is the rest of the connections have to be rearranged. But a rearrangement does exist if M is greater than equal to N to connect an unused input terminal to an unused output terminal. However, if M is greater than equal to 2n minus 1, which means if M is even greater, right? So this was greater than equal to n and this is greater than equal to 2n minus 1. We can do exactly the same without rearranging the rest of the connections, right? So the rest of the connections don't have to be rearranged. Without any rearrangement, we'll have sufficient space in the network to realize a connection between an unused input and an unused output. Now let's look at the butterfly. So the butterfly, as I said, is not really high radix topology because if you look at the Clos, it was a high radix topology, right? So in a sense, one of these switches, it is being connected, each one of these guys is being connected to M switches, right? So basically, this connection is there. But this is technically not happening over here in a butterfly because we have two inputs and two outputs. So here we have 8 nodes which are the primary routers. So they are the producers and consumers of data. So as was the case in Clos, they are the producers as well as the consumers. And then you have these three columns of internal nodes which are actually the switches. So I can write this over here. All right, that these are the three columns of internal nodes, which are the switches, right? So we have column 1, column 2, and column 3. So the idea is that again, it's not a high-radix network, at least the way it is drawn here. These are 2 cross 2 switches, but the switches do an important role. So the first, you divide the network into 2 parts, right? So let's say you divide it over here. So each switch basically keeps the message either in the current part or sends it to the other part. That's what the first column does. That it keeps it either in the first 4 or in the last 4, right? Either in the first half of 4 or in the second half of 4. And then the next switch basically, further divides it. So what it does is that again it keeps it either in the first 2 of that 4 or in the second 2 of that 4, and the last one again, makes a choice between 1 and 2, 3 and 4, and so on. So what you can basically see is that in this case, because we have 8 nodes, what we are doing is that let's say given an input 6 and it needs to go to 2. So the first decision that needs to be made is, where does 2 lie? Is it in the top 4 or in the bottom 4? Bottom 4, okay, we send it over here. Then we see, where does 2 lie? Is it in the bottom 2 like 1 and 2 or 3 and 4? It lies in 1 and 2, fine, it goes here. Then where does it lie? 1 or 2, it goes here. So that is how the network is connected. And clearly over here, we can achieve many parallel flows. But again, as I said, the bandwidth of every switch is limited to 2 inputs and 2 outputs. If let's say we were to have 16 nodes, then basically we would have had to add one more column, which would have said first 8, like the top 8 or the bottom 8. So pretty much, as you can see, we'll have log n columns over here, and this is log n to the base 2. So because we have 8 nodes, we have log 8 to the base 2, which is basically 3 columns over here. Of course, efficient implementations with high radix routers exist, which is why butterfly networks kind of show up here in the first place. But as I said, the way it is drawn, it is not high radix, but high radix avatars of the butterfly to exist. So now let's look at the summary of where is it that we stand in terms of the topology, number of switches, links, diameter, and bisection bandwidth. So the chain and ring clearly don't have any internal nodes or switches, so this part is easy to understand. The number of links in a chain is n minus 1 for n nodes, and for a ring it is n links for n nodes. The diameter in the chain was high because we had to go from one end to the other end, so the diameter was high, whereas the diameter in the case of a ring, which was from here to here, was half, roughly half, right? So in this case, we are ignoring ceilings and floors and a plus one, minus one over here. So a little bit of ignoring we are doing. And the bisection bandwidth in this case is 1, in this case is 2. That should be clear. So the number of switches in a factory, assuming n nodes and n is a power of 2, is n minus 1. This we know, right? Whoever has studied binary trees kind of knows that. And the number of links again is 2 times that, right? So why is that the case? Well, an assumption is of course being made that the size of each link is equal to the number of leaves in a subtree. So that is how this comes, right? And the diameter, as we had argued then also, is 2 times log n, because it's log n to go up and log n to come down. And the bisection bandwidth is n by 2. Well, why? Because of the assumption over here that at the top of the factory, close to the root, right? If I were to cut, sorry, if I were to cut, then basically, this would cover n by 2 nodes. So the number of links I need to cut would be n by 2. All right. So similarly for a mesh, again, there are no internal nodes. For a mesh, torus, folded torus and hypercube, we don't have internal nodes or we don't have switches. But again, we have different numbers of links. So for a torus, of course, it is 4n. Well, why? Because every node has a degree of 4. So it'll basically be the degree of a node divided by 2. So 4n by 2 is 2n. But in the mesh, we don't have that many links because for rims and corners, it's kind of reduced. And again, the diameter in this case in a mesh is like corner to corner, right? So in a torus, it's actually, it's not corner to corner, that's fast, but it's from a corner to a center, right? And again, in the case of a folded torus, it is again corner to corner. So that is why the root n factor comes over here. And the bisection bandwidth is 2 root n because you pretty much need to snap links along a row or along a column. So for the hypercube, we have seen that. So what we have basically seen is that the diameter is log n because the Hamming distance, the maximum change in the Hamming distance could be log n. Because for n nodes, its binary representation has log n bits and every bit may change. The bisection bandwidth is n by 2. Again, because you need to cut. So this was discussed in that section. And then for a butterfly, we'll have n log n by 2 switches. N log n by 2 is not very hard to visualize. We have log n levels, log n columns actually, and each of them has uh, n by 2 rows. So we have n by 2 times log n is n log n by 2. Number of links will come down to this, and the diameter will again be log n plus 1. So actually the diameter is kind of the same between any pair of nodes because you have to traverse through the switches, right? And basically you have to go from column to column to column. So there are log n columns, so it is log n plus 1. And the bisection bandwidth in this case is n by 2. So this is a short summary of the networks. I'm not saying that all of them are used in an on-chip NOC. Some of them are used and some of them are not used, right? So basically a chain is not used, but a ring is used. A factory again, no. But mesh, torus, folded torus, yes. Hypercubes, no, but some variant of butterfly networks and Clos networks, albeit flattened. Flattened means, converted to a 2D topology, right? A 2D or 3D with two layers, roughly. So things of that nature are actually used. So now we have discussed the broad overview of an NOC. So this lecture will end over here. The next lecture will look at some fundamental results in message transmission. And if we get the time, we will cover routing. And the way the chapter will progress is that we'll discuss the design of a router, which is a key idea for us. How to kind of co-design the NOC with the last level cache. Again, that's something of fundamental concern for us. And finally, how do you benchmark an NOC? So what is benchmarking? How do you kind of decide whether an NOC is a good NOC or a bad NOC? Basically, you would run some programs and you would like to figure out, right, that whether the NOC is well designed or not in terms of its runtime performance. So look, the diameter and the bisection bandwidth, these are pretty much design time parameters. So they don't change. So once we decide on the topology, we decide on the diameter and the bisection bandwidth as well. But the point is that many other aspects such as the router, the design of the router, routing protocol and so on, including the kind of workload you're running, determine the performance aspects of the NOC in the sense how many messages it's able to send, its throughput and so on. Throughput and latency primarily. So I would say because we are not dropping packets, I won't use the word good put that you would use in a traditional networking scenario. But essentially throughput and latency, where throughput is the maximum number of bytes per second you can send between two pairs of nodes, and latency is how long it takes in terms of, let's say, clock cycles. So we'll discuss these performance aspects with synthetic benchmarks in the last part of this chapter. But the first part of this chapter, which was this lecture actually, was to convey what all an NOC is about and basic topologies and basic ideas, right? So that has been done. So we are kind of well poised to look at more advanced topics in the subsequent lectures of this chapter.